Welcome to the introductory video about uniform circular motion. This is in the topic of two-dimensional motion, but I waited to now to talk about universal circular motion so we could have some other topics like forces under our belt before we got to it, because it's not an incredibly complex topic in some senses, but in other senses, and in other ways, it really is. So I'm going to show you a bunch of videos and animations here, and we'll talk about it and stop and have some questions on the way. So it's in chapter 9 here, and you'll do the reading afterwards, after we have class. So here is an animation with a fairly good explanation. We'll stop and go through some things, but here's someone else talking for a minute.
In uniform circular motion, an object travels around a circle at a constant speed.
So notice our speed is constant, but from this outside frame reference, we're traveling in a circle.
The velocity of the object is the rate of change of position with respect to time. This velocity can be estimated by examining the change in position over a short time interval. The instantaneous velocity is then the limit of this estimate as the length of the short time interval goes to zero.
So you get this velocity that's tangent here to the circle, tangent to the radius. And as
the direction of the velocity vector is always tangent to the circle.
So if you notice here, your velocity is constantly changing because the direction is constantly changing. So it's not that the speed is changing. That can happen, and that's a very interesting situation and brings about some other complexities which are really, really interesting. For right now, we're going to say the speed stays the same, but because you're traveling in a circle, you're constantly changing your velocity. What's also interesting here, if we look at a different simulation, we've got two bugs. We've got a ladybug and I don't know what the green bug is supposed to be on this turntable, and we'll let it move at a constant rate. Notice the velocity vectors here. They are tangent to the circle, but the green bug's velocity vector is larger than the ladybug's because he is further out on the circle, and thus has to have a greater velocity because they have to share that common time. They both have the same amount of time to get around that circle once. He's got to travel, the green bug, a longer distance, so it has to have a higher speed. If we speed it up even more and reduce that time, reduce that period, increase that frequency, we can see that they increase even more. If we slow it down again and even reverse it, notice the velocities reverse. Alright? If I move the ladybug directly to the center, if I can get her directly in the center, and now I move the turntable, notice she has no velocity because that center of mass is right on the center. So she's just rotating. She's not actually traveling any distance. If we move her back out again, you can see that again we're going to get that velocity based on not only how fast you're rotating, but also how far from the center of that circle you are, because you have that same amount of time to go around. Let's look at something else that's going on here.
The acceleration of the object is the rate of change of velocity with respect to time. The acceleration of the object can be estimated by looking at the change in velocity over a short interval of time. The instantaneous acceleration is then the limit of this estimate as the length of the short time interval goes to zero.
So notice that acceleration is pointing towards the center of the circle. That also makes it perpendicular to the velocity. Thus, it just doesn't change the magnitude or how big the velocity is, or what we call speed, but it does change the directionality of it. When we talked about two-dimensional motion, I showed an animation of a car being turned. Any time that acceleration is exactly perpendicular to the velocity, we know that perpendicular vectors don't change the size of each other. Thus, It doesn't change the size of the velocity, only the directionality of it. And that's what's causing this ball to be able to change its velocity.
The direction of the acceleration vector is always towards the center of the circle.
So always in there. And if I pull out our ladybugs here again, and now I show the acceleration vectors, you'll notice they're pinned right there towards the center because they're not changing the speed, they're not changing the magnitude of the velocity, but they are changing its directionality. If I speed this up, again, look at how much larger they get. So that rate of change of that velocity, that acceleration now, is also related to not only where you are on the circle, but also how fast you are turning, that speed. Those combine to give you the magnitude of this acceleration, but it always must be towards the center. One way I like to look at this is this kind of simple animation. Let's start that again for you. Oops. Now it's just being difficult. So we'll close this and we'll open this on its own. Get that out of the way. So we're going to approximate a circle. So as the ball changes direction, as it had a green velocity vector this way, now it's got one that way, that change would be right in between those. Remember, the change would be adding the two together. One way to think about it is adding them tail to tail. As we add more corners there, notice that these changes, this purple, are always radial. And if you think about a circle as being constantly changing direction, rather than this incremental change of direction, you get a constant change in direction. That's why that acceleration vector, that constant change, is towards the center. All right? And that kind of takes us up through the first little part here, through its centripetal acceleration and uniform motion. Now, where it comes in interesting is we know that if something has an acceleration like these bugs do, that acceleration has to be provided by a net force. So what's providing that net force in these cases? If the acceleration is center pointing towards center, and that's why it's called centripetal, by the way, because center, tripetal, seeking, center seeking. Why is it, therefore, going toward what is providing it, what net force? And that's where we come into what's called centripetal force. And, here we have the animation of a car going around a circle. It, of course, has its weight down. It has a normal force up. And what's holding it into that circle, what's providing that centripetal force, is friction. Now, because it has that acceleration, something outside the body must always provide the net force. And the net force in uniform motion, circular motion, is a centripetal force. So it isn't just something, it isn't because it's going in a circle it has centripetal force. No. Because it has a net force on it that's always pointing towards the center of the circle, therefore it is going in circular motion. If that force isn't there, from the outside point of view, the object's inertia is going to carry it in a straight line. So if suddenly this car hit ice, it would go off in a straight line and not continue in the circle because that centripetal force, that friction that is causing the allowing and causing and creating that circular motion, would no longer be there. If we look at this, another situation of this, which is, let's put this car now onto a banked track. And this is interesting because now that net force, as you see here, is still towards the center of the circle. The weight is directly down, but the normal force is now tilted. So if I can do this really quick, there we go. You can see a component of the normal force goes and creates part of that net force, that force needed for centripetal motion. And this is why corners on racetracks, exit ramps, highways, anywhere that you need it, are banked. Because here, if we take a perfectly designed corner, we do not need friction. If you take a flat corner, like on a normal, like driving down 1A, you take a corner, turning onto another street, that's not banked. If you don't have friction, you're not going to make that corner. But if you're coming off the exit ramp, or you're driving on a racetrack, you don't want to have to rely on friction. You want to be able to rely on a component of your normal force providing that net force, that centripetal force, as you go around that corner. And that's why we bank it. And notice that it's still pointing inwards, and the normal force, because of the bank, has that angle inwards. So remember, the normal force is always perpendicular to the surface. So it's like it's on an incline sideways. If it wasn't moving, that net force provided by the normal force and the weight would cause it to slide down the bank. It has to keep moving. There's actually a really interesting thing in racing called a progressive banking, which the banking changes on a curve, so that based on how fast you're going, you can go at different heights along the curve. Now, so what happens when we want to do like a loop-to-loop? That's another interesting one. Let's bring up an animation of that. When a car wants to go around a loop-to-loop, whoops, I don't want that because I have so many files open. So we're going to play this one again. You can see the car here. Car is going to come in, and of course it has a normal force on it, is what they're showing you here. As it goes up, that normal force changes. And right at that top, did you notice that normal force, that yellow, is 0? So what's providing the centripetal force? Well, the weight of the car is providing the centripetal force. Where when the car was down here to go in that circle, the normal force had to provide the centripetal force. The weight was pointing in the wrong direction. In fact, the normal force had to provide more than the centripetal force because it also had to counterbalance the weight. And if we go back here even further, now before they get in the circle, they're pretty much even though the simulation doesn't show it that well. But you can see, as you're going, there always has to be that force pointing towards the center. And if it's not large enough, you're not going to make the circle. Let's look at something else that's very interesting here, though. And this is down here in number 9. And this is a way to look at and explain why when I'm in a car or going in a circle, it doesn't feel like I'm being pulled to the inside. It feels like I'm being pushed to the outside. And that is because that's what's called a fictitious force. Fictitious because it doesn't actually exist. A great way, I bring up this little clip here, made, I'm assuming, by a student somewhere, and it was their explanation of inertia. So watch this for a second, because it's a good explanation, and we're going to use it.
This shows inertia because even though the car stops moving, the ball continues to roll. This is because no force has stopped its motion until it hits the end of the ball.
So from the outside frame of reference, from us watching that car hitting the wall, that is a great explanation and completely correct of why that ball keeps moving. And if the ball was in the front of the car and the car suddenly accelerated, that ball staying there until it ran into the back of the car would also be a great explanation of inertia. And it's true. But what if we're in that frame of reference? We're sitting in that car and it accelerates. We see the ball move backwards, which in our frame of reference it does. But what is giving it that acceleration backwards? What's happened here is we've moved out of the inertial frame of reference. We've moved into an accelerated frame of reference. And in an accelerated frame of reference, we can no longer have that relationship between being able to measure accelerations and causes of them from different frames of reference. If we have an inertial frame of reference like the Earth, and we observe this car going, and we see the ball moving backwards, there must be something causing that ball to move backwards. Our explanation in the car is that there is a force backwards on it, which there isn't. It's due to its inertia. But that fictitious force that we would have to have in the accelerated frame of reference to prove that the ball was accelerating doesn't exist. And from our inertial frame of reference, we see that it doesn't exist, and the explanation is through inertia. This happens whether we're looking here at the ladybugs, or we're looking at the cars going around the circle, or any of those, because we have that need to have a force to explain the acceleration. And that force is the centripetal force, pulling them inwards. To them, because their inertia wants to continue in that straight line, they want to be in an inertial frame of reference, not an accelerated frame of reference. That fictitious force feels as if they're being pulled outwards, when they're not. They're being pulled into the center because of the net force on them causing them to accelerate in the center. That can also be shown. Here's another little animation of it. Notice the weight versus the normal force, and as this goes around in the circle. This can be used in many ways. One example that they bring up here in your book is causing artificial gravity, because you can use the normal force providing your centripetal force to create a feeling of gravity, and that's spinning. It also, we have the example of the loop-to-loop like we were just talking about, but it is a fictitious force because it is pointing towards the outside, but in that accelerated frame of reference, it feels like it points towards the inside. Something really neat you can do to investigate this type of idea is actually next time you're on a school bus, bring a tennis ball, put it in the center of the aisle, give it a try, see which way it moves when that bus accelerates. You can also do the same thing with a helium balloon, and it'd be interesting to see what your results are on that. Alright, I know this one's been a little long. I'll see you in class.